Okay, that's no, the main thing that we didn't get into yesterday was the unset boxes at the end. And I'm sorry, I don't have my sheet that has it in big letters, so that we can't get it very well on the TV camera. Let's see how much you can enlarge just for fun. I always wondered about that. Maybe it's going to be you get up like that, and then okay. Here's an unset box. Okay, Y34, and it's yeah, very delicate at this high magnification. But that's said right there where my thumb is moving. It says unset box, and what it means is that while you're doing an alignment, the glue in the box hasn't been set yet. So even though it says the glue has been set to some funny thing, that's really just to be ignored. While an alignment is going on, TeX is just holding these boxes unset until reaching the final end of the alignment, at which point the maximum width of every column will be determined, and then each box will be set to be equal to the maximum width. If you ever stop TeX in the middle of an alignment, you can see how much it knows about the formula so far. There will be these boxes that are almost in their final form, but they're unset as a Y34, and then you go to the next page, and it'll turn out that the box eventually does get set, and Y34 occurs here, and this time the glue has been set to 0. That must have been the widest one in that column. The Y1 has a glue set of something to stretch it out a little bit to make it equal in that column. I think there was a fill or something in that column to make it work out. So finally, on the last page, you see what happens after things got set and the alignment was finished. But the previous page showed the intermediate step of the thing. I also want to mention the way some things appear before and after being in a paragraph, like a send. When we had a send, it was in the middle of a paragraph, and then after it got sent to the output, the send appeared after the line that contained the send. Let's see, we have that shown. That was probably the thing that went out to page 1. No, I'm sorry. That's not. It's a lie. It's not true. The send doesn't get after. No, sorry. Top insert gets moved after, but we didn't get to see that. So I'm not sure we have any evidences of that kind of motion in this example. No, I guess not. Well, so the main point of all this was that TeX is really building horizontal lists and vertical lists, and in math mode it builds trees as it's reading your text, and then it puts them all together according to these rules. And so we got to get to know that part of the tool if we're going to see how to bend it to other applications. Next thing I want to talk about is a little bit more about the way the paragraphing mechanism works. I mentioned hanging indent last week, and I mentioned looseness. Just a quick review of looseness. Here's an example of a paragraph that was typeset with 4 different degrees of looseness. At the very beginning, we have it set loose -1, which meant that this is a little tighter than the optimum. This is the optimum according to TeX rules for that particular paragraph. This is a Grimm's fairy tale. Don't bother to read it, please. And then the same paragraph again with saying loose +1 makes the thing 1 line longer, and this is when it's +2. Now, if the looseness is growing slowly, you don't mind it too much, but it would be very shocking if you went from the first paragraph to the last on the same page. Can we have this? Just look at the page from afar. A gradual loosening up is tolerable, but no, I'm sorry. I'd like to see just the whole page, but only the spacing on it, not the words. Yeah. You see. So if I put the bottom part next to the top, you see it looks quite different. But you don't notice it if it gets slowly. But that's to avoid widow lines if you have to do some fine tuning on the end and you're really becoming typographically concerned about things. Some special job for a special occasion, if you want to tune it up. Another thing, these paragraphs can be made in any shape you like. So here was a first example of such a shape. Take this triangle, for example, is Blaise Pascal talking about the triangle, and and then Michael found Galileo talking about circles. So this just demonstrates that text paragraphing mechanism will also find the optimum breaks for arbitrary sizes that you might want for some important application. Usually that's just for playing, of course. But the fact that it takes the paragraph as a whole means that it can do what might seem as amazing look-ahead feats. Now, I'm going to talk about the details of how we can do this next example in a few minutes. But let's first see what it is. This is the same paragraph in which I've done ragged centered instead of ragged right. Can we have this on the screen, the top part here? Just get up on this. Now this took that same paragraph and it broke it up into a number of lines which was as few as possible, and given the width that we wanted, we specified, and then all as equal as possible, and centered them all. Now in order to get that effect, it was all done by the paragraphing routine, and you could write a macro, and we'll talk about it later on today, how this would take a paragraph and it would center it on the proper number of lines, essentially minimizing the maximum white space on each line coming in from both sides. But this would all be done by the same paragraphing mechanism, just using boxes and glue. You type something in, it goes in as a horizontal list, and the paragraphing mechanism that's used for ordinary paragraphs would just happen to do this to the text. Now, other things that we aren't going to talk about in detail, but they're described in the paper that Michael Plass and I wrote, called, that's why our names are on the top here, you see. And the paper is called Breaking Paragraphs into Lines, and it's going to appear in Software Practice and Experience in about 5 months from now. This example shows an example from Pascal programs, and it's another example of how the paragraphing mechanism of TeX can be, and a proper combination of boxes, glue, and penalties will do unusual feats of typesetting. The bottom example, this is exactly the same text, is a program taken from the Pascal manual. And in this example, actually every line in this example is one paragraph in the TeX source file for this thing. And the indentation of each paragraph has been determined by macros, and we have a preprocessor that will take in any syntactically correct Pascal program, output a TeX file, which will list like this. It can, it chooses the bold and spacing in formulas and Roman and italic and everything by itself, and that's all put into the TeX file. Then then what you have to tell the TeX file is what's the column width that you want. And from the identical TeX file that listed this will also produce this if you say the columns are narrow. And so, well, each paragraph is treated separately, but you'll notice that the macros were set up so that they would break up in reasonable ways, and they would continue lines. Like a continuation line, I think, is two indentation marks over from where the next line would start, and so on. This TeX file is defined in terms of a few macros that are it's called algol.tex on TeXsys. It's a set of macros that are useful for displaying algol-like programs and breaking them according to the constraints of the margin at hand. So, in other words, this preprocessor does not know what the margins are going to be. It puts out exactly the same TeX information, for all size margins. It's the paragraphing mechanism of TeX that calculates boxes, that calculates how to break lines, that actually decides this. Arthur?
Do you do nice things for breaking this paragraph as you would for a math formula?
The math formula is, in fact, most of these are math formulas.
But I mean, will you prefer to break after a plus as opposed to before it?
Yeah, you never break before a plus. It's because it's done by there's a math formula. If you look at that text source file, it has dollar signs around things. Okay. So this is, but it also includes this ragged right feature and so on, all in there. Now, another example of what you can do with the right combination of boxes, glue, and penalties is probably the most complicated example I've ever handled so far is this one, where we have three examples. This is based on the indexes to math reviews, and these are three examples all set from identical text source, each involving three paragraphs, and the paragraph algorithm that takes a paragraph, finds the optimum breaks, has typeset these things from exactly the same source file, except that we changed the width of the lines so that the breaks would occur in different places. Now notice what these index entries, they start out with a ragged right margin, and then they have these leaders, these dots here, which sometimes occur at the end of a line, sometimes at the beginning of a line, and sometimes in the middle of a line. And at the end, after the leaders, then you have left, then everything is flush right, and it's left ragged. And all of these things are done by boxes and glue inside of the in the input here. Now that, as I said, was the hardest so far the application that I've handled with these primitives that TeX uses in its horizontal list. But it shows that unsuspectedly powerful ability to handle typesetting problems that don't look like ordinary paragraphs out of Grimm's fairy tales. Still, you do it with exactly the same method that was used to typeset Grimm's fairy tale. Now, how can you use this idea of boxes and glue and so on, which is kind of an optimizing method, an indirect method, rather than a direct method, which says do it line at a time and make a decision one line at a time. In order to understand that properly, you have to read carefully the fine print that says what is TeX optimizing. TeX is trying to optimize what it calls demerits over the paragraph, and the demerits are associated with each line. The demerits on each line is something like the badness of the line plus the penalties on the line plus 1 squared. And so a line has badness associated with it, and it has penalties associated with a break, and then there's this other constant 1 that keeps you from preferring long constructions to short ones. Now the badness of a line, well, the penalties are easiest, so I'll take the penalties first. If a line ends with a hyphen, for example, then there's a penalty for hyphenation. If there are two, let's see, actually there's another add-on to the demerits for extra kind of penalties, like 2 hyphenations in a row, you get an extra penalty added on. Or a loose line following a tight line, you get an extra penalty added on. A few more demerits. But most of the contribution comes from the penalty associated with the line itself. Starting at one point in a paragraph, ending at another, then you pay a penalty for how bad the space for breaking at the right-hand margin, and the badness relates to the spacing in that line. So the penalty is generally associated with the right margin, and typically if the line broke at a penalty, then that's what P is. Penalties in TeX, if there are 1,000 or more, it means that you're not going to break the line at all. but 999 it will break and pay a penalty of 999 in this formula. The badness of a line is approximately 0 if the line is near, if the glue didn't have to stretch or shrink very much in the line. But the badness gets to 100 if the line had to shrink its maximum amount of shrinkage, or it's 100 if the line had to stretch to the specified amount of stretching. Now, a line is never allowed to shrink more than the maximum amount of shrinkage, but it is allowed to stretch double. And if it had to stretch, or any amount, it can stretch much more than if you say the glue is like 10 points plus 10 points, then you could stretch that to 100 points. If the 10 points of stretch were actually multiplied by 9, you get 90 points of stretching there, but that would be very bad. So the badness is something that gets very large when it has to stretch a lot. And the actual formula is proportional to the cube of the amount of stretching, so that if you stretch by the full amount, the badness is 100. If you stretch double that amount, the badness is 800. And,
question?
Yeah, questions?
Does that mean you can't force minus letter spacing unless the font designer has set things up?
You can force what?
Minus letter spacing, so that unless the font designer has...
To crowd letters together, that should be done in the font design, and Metafont does that for you. That's right, but we don't know. In fact, typographers don't like that, and so Tech took their advice. The tightest line you can get is to squeeze down so that the glue is down to its maximum amount of maximum negative amount, and that would be a badness of 100. If you got a line that didn't fit at all, so that you wanted to shrink it more than the total amount of badness, then the badness is actually considered infinity. That's so that minimizing the total demerits, you would find that you try to avoid infinitely bad lines. You can overfull box if there's no way to do without an infinitely bad line without exceeding the badness equal to 100 times the J par. So if J par is 8, it'll never allow badness to get more than 800. If J par is 2, which is normal for our type restrictions, then you never allow the badness to get more than 200. And you don't consider any possible breaks that would be worse than that. If you want to, that's quite reasonable, because some lines are so intolerable you don't even want to bother considering them, and it speeds up TeX's algorithm if it restricts itself to considering only lines of bounded badness. Now, so we get badness and penalties, and then we square the whole thing, and then we sum that over all lines, and we find the best way, the best score for the entire paragraph. So now we have to, when we have our applications, we have to find a way to look good from the standpoint of this formula. Exactly the same method that's used in horizontal lists to make paragraphs into lines is used also in vertical lists to make lists of lines into pages, except that TeX doesn't optimize over your entire document to find the best way to break pages, to break your whole document into pages. TeX only will optimize over a whole paragraph to find the horizontal breaks, but for optimizing over the whole document, TeX doesn't do that unless you use a special version that Michael has for experimental purposes here, which goes in 2 passes. The first pass writes out information about what the document contains. Then comes an optimizing routine that figures out the best page breaks, and then you go through the whole TeX run again with reading in a break file that uses that says here's where to break the pages optimally according to minimum demerits, and the second pass produces that, and Michael's thesis will describe this in detail. Now, legal breaks can occur in a paragraph in 2 cases, maybe 3, depending on your definition of a case. The first case is when you have glue following a box. glue following a box is the legal break. You break at that glue, then the glue goes away, and the box is the end of the line. The second case is you break at a penalty, and anywhere where someone specifies penalty, that's a legal place to break. Okay, with that penalty being paid. So you say penalty 0, that says here's a place to break without any penalty. Penalty negative 100, say here's a place to break and you actually win. And in fact, we don't use that formula when p is negative. When p is negative, it's b plus 1 squared minus p squared when p is negative, because we want it to be a monotone function of p. So we want to actually, take away demerits if p is negative. This is p is positive, and this p is negative. As I said, if the penalty is 1,000, then it's not allowed as a break at all. That's in order to insert a glue which you don't want to break. So you have a box, and you want to follow it by glue, but you don't want to be able to break at that glue. So you say box, and you say penalty 1,000, then you give the glue. And glue can never break except if it follows a box, and you can't break at a penalty of 1,000, so you didn't have any ways to break there. So that's the idea of penalty 1,000. Now there's one other case of line break, and that is where somebody actually wrote line break or eject in his paragraph, and that will force a break. That's like a penalty of negative infinity. Very good place. So every such place is forced to be a line break. Now you get to use you get to after you experiment with these tools, you get to appreciate the power of these simple three concepts of boxes, glue, and penalties, and combining with demerits. And it took me about 2 years before I learned some of the things you could do with them, and probably was almost a year before I realized some of the first non-obvious applications of the method. So the fun thing for me was that I made up these rules just so it would work for ordinary paragraphs, and then I found out months later that without changing my algorithms, I was also able to do Pascal and all this other stuff. One thing that arises fairly often in applications is that somebody likes to say, I'd like to end the page now and start a new page if I'm near the bottom of the present page. Okay? Try to, and then if I move to a new page, then I'll just leave the bottom of the present page blank. So it's sort of a conditional look to see if you're near the bottom of the page, then fill that page and start a new page if you're near the bottom. Otherwise, get start working on the next copy. How do you build that in? Well, fortunately, it's very simple. You say like this: this is in vertical mode. At a point where you have a decision like this, you say v fill. Let's say with 1L. This means skipping. This is the same as v skip 0 point plus 100,000 points. And then you say penalty 0, for example. It says it's legal to break after the v fill. And then you can say v fill negative, which is v skip 0 points plus minus 100,000 points. Now, I forgot to tell you one important thing, at least one. That is that at a break, then you wipe away all the glue and penalties after that, from the point of the break on until you get to a box afterwards. So glue and penalties disappear at a break. Now let's watch what happens then. We had some text up here, some text down here, and what does this mean to the page layout routine? These three lines specify an optional break and start a new page. The reason is you either break at this penalty 0 or you don't. By the way, I should put Okay, I could break at the V fill here, but it would, it's always dominated by breaking at penalty 0 because having a little more stretchability isn't going to hurt. So the formula for demerits, for badness, will always be at least as good by breaking at the penalty 0 as breaking at V fill here, so I don't have to worry about considering what happened if I break at this V fill. So since it'll always choose the best one, when Tech is breaking pages, it takes the best one based on the current one page at a time. So it looks ahead and keeps on going until it gets into the next page, until there's no more, until the badness now gets infinite, so that there's no more way to squeeze anything more onto one page. At that point, it chooses the best of all the available breaks and outputs that page and starts over again. So we have to consider two cases. Either it breaks at penalty 0 or it doesn't break at penalty 0. If it breaks at penalty 0, then the glue following it is also wiped out. And so the net effect would be break the page here, fill the previous page, start a new page. The other alternative is it doesn't break at the penalty 0. In that case, the V fill followed by V fill negative is a no-op. This plus negative 100,000 points cancels with this, and so any stretching here is taken away from there, and the glue adds up to 0, and nothing happens. And so the thing continues. So now Tech is going to consider two alternatives, either to put this next business on the same page, or to move it to the next page. And the difference between the alternatives is based on how well this thing that's coming up fits on that page without any flexible stretching allowed. If that second thing fits rather nicely, then we'll have a good situation, and two things will go on the same page. Now, one thing, for example, the way I use this, if I have a bunch of items, I put them into boxes. So that this box is actually a big box. So this box will either fit on the page or not. And so then then it will take the break here if and only if this thing fits on the page. But putting it in a box means you'll never break it between pages. Arthur?
What happens if you just goof up and put a V-fill neg in the middle of somewhere?
If the total stretchability on a box that you're trying to set the glue of is negative, but the box was already short. If the box is short and you want to stretch it, and the stretchability is negative, it passes, I think, and just lets the glue to 0. Similarly, shrinkability, if the total comes out negative. Yeah.
Going plus minus 100,000 points is not the same as going minus.
No.
100,000 points. The idea that the plus is to cancel out a plus or positive.
Is giving the stretchability, and the minus is giving the shrinkability. Yeah.
Merely to cancel out a stretchability somewhere else.
That's right. So you can have negative stretchability. And the total should always come out positive, though, if you don't want some weird thing to happen. And it always will in a situation like this. So. In fact, if you monkey around, if you just put arbitrary things in there, of course, the optimum would not make any sense. So the optimizing algorithms do assume that there's some reasonable restrictions satisfied on these glue. Otherwise, they don't bother to optimize under weird cases. All of this is spelled out in very great detail in our paper. Okay, now this thing also applies in the horizontal direction. Yeah?
Yeah. Presumably, in the setup you have here, the page will now be broken so that there is no badness.
Almost no, because the V-fill has so much stretchability that there's almost no badness.
If you wanted to sort of work a little bit to try to fit in something, could you simply reduce those? I guess you've got 100,000 points. Could you reduce them something like 60, 70 points, and then it would work?
Yeah, you can play with this number. You can also play with this penalty number, and gives different effects. So the amount, you can say, well, maybe I should pay a penalty for a short page. Maybe you don't, maybe you'd like to discourage it. Maybe you'd like to encourage it by making the penalty negative. And you can twiddle also with the badness by this calculation. That's why you want to go to your formula for demerits to find out which optimizes. Of course, actually just the in the case of pages, it's a monotonic with penalties, but it chooses the. I think in the case of pages, it's just B plus P is minimized. Every page minimizes B plus P over all page breaks for that page. Okay, now.
A question, Don.
Yeah, another question.
Yeah, that example there where you have the conditional page break seems to be a good one application that I can see is to make sure that like a section heading is tied along with the first few lines of a paragraph.
That's right, because typically a section, when you start it out, you'll say chap or section 3.1, and you give a title, and then the text of the section will say we will now or we shall, etc. And there will be a little bit of space here, V skip 3 point or something between the title of the section and the beginning of the text of the section. You don't ever want to break there at that place, so you would say penalty 1,000 in front of the V skip 3 point. And that forbids a break there. That will force these lines coming in here. Furthermore, there will be to avoid a widow line, there will be an extra. The widow line penalty will appear after this line, saying we shall, and so there will be. TeX will discourage breaking after that line. So it will want to get at least this and 2 lines of the paragraph in before it even considers a reasonable break. And then there will probably be some stretching or shrinking involved that will make it a little bit undesirable compared to this, maybe not. So maybe you want to put this penalty a little higher. Yeah.
Just in terms of numbers, what would be considered a large penalty for a page break or a small one? About how much?
Well, you see, 100. You have to think of it this way: 100 means the maximum stretching of all the glue, or the maximum shrinking. And so a penalty of 2. If you're saying a penalty is negative 200, you're saying that you don't care if somebody stretches pretty much. You'd rather break here anyway. If you're saying a penalty of plus 200, you're saying this is going to be so bad that probably it'll dominate other effects. In other words, you wouldn't want to do this unless it was necessary to avoid 200 badness in some other break. So that's the order. The 100 is the round number that sort of means that limit of tolerance. And the fact that badness, when you're doing it in one paragraph, is cubed just means that it stays near 0 when the shrinking is near 0. Okay, now before I go on, I wanted to give you some homework, and this is a handout that you should pick up. The idea is there are 6 problems here that if you can solve these 6 problems, then you can be considered eligible for a wizard's license. Making these these 6 problems seem to cover the main points that are necessary in macro design. And tomorrow, I'm giving them out today. Tomorrow I'm going to discuss hints about them if somebody has questions about them. And Thursday I'll describe the answers to them in just overall, and I'll also hand out answers on Thursday. Each of the problems can be solved with just a few lines of TeX coding. I'm not going to say exactly how many, but not too many, fewer than 10, I think, in each case. And then on Thursday, I'm also going to give out the challenge. Maybe even on Wednesday, I'm going to give out the challenge problem that I doubt if anybody will solve. But just for those of you who find these 6 too easy, would like to work on the challenge problem, we'll be talking about that on Friday. The main ideas, though, in these 6 problems are to focus on one aspect of designing macros for users, as you'll see. The first problem is the simplest one, but I don't guarantee that the others are in order of difficulty. The first problem is at the top of the page. Can we have it on the screen, please? This part here, and it was based on something that came up in last week's class. We had at the left of a page there was a dash that we wanted to get into the margin, and so the source file just said hide and put the dash in. Yes. So you have to define for this one, just define as control sequence hide. Now this is a fairly common thing in typography. If you're ever doing poetry, for example, you have lines of a poem. Often, if a line starts with a quote mark, that quote mark is supposed to be brought out to the left. And so you would also put hide in front of certain punctuation that goes at the left of lines when you're lining up lines of a poem, or in this case, this was at the left margin of a book. So design a macro that does this hide. That's problem one. Problem two was another one that arose in that same book about Stanford. And here was the output, and the input is shown below it. Your job in that one is to design a macro called fancy, which set the S here and did that right. Now, I should tell you that this S is 30-point type, and the other are 10-point. Question?
Should fancy have to work independent of what baseline skip has been set to?
No. You can assume the baseline skip is from basic right now. It's possible to determine the baseline skip. As you probably know, you just could say, for example, V box of H box null, H box null, and then you look at the height of this box. So you save this, and you look at the height of this box, and that's the baseline skip.
The difficulty, though, is dividing the baseline skip into the height of the letter to figure out how many lines you want to go down.
No, I'm assuming that this letter is that this letter will go down by the same amount as the baseline skip. So you can assume, if you want, that you're in 10-point type and that it's dropped down, that you've got a 30-point letter, but it's not really 30 points high. But what they call a 30-point size. That would include descenders and a little extra spacing, and then that you bring it down to things as shown there. Anyway, and it should work just assuming that there's a letter following the word fancy.
Question?
Yes.
On that example, you have bring it back up. Is the baseline spacing under the S still the same, or is there a change? It's hard to tell on the screen.
All of these lines are 12 points apart.
Okay, that's the question. I didn't know if you
I
put a
didn't
little
touch the
extra.
baseline skip at all. Fancy is a 2-line macro. One line if it's long enough. But Arthur?
Is it supposed to work if S is an I?
If S is an I, it depends on the size of the letter. A wider letter would move over a little bit more. But if it says I am, the word I, well then of course we would actually have a space probably there where the E is now. Okay? Well, that's the next exercise. The third exercise is one taken from Math Reviews, and again I gave the source at the bottom that generated these 2 lines. Notice what the lines explain the problem. You're supposed to design, in this case, a macro called signed, and this is to go through the paragraph. So the text paragraphing routine will do the right thing. Okay. It's very much like what I just told you in vertical direction, right? Except this is in the horizontal direction. This is the end of a paragraph. The end of the paragraph is the flush right in these cases, yeah. So at the end of signed, it is assumed that that's the end of the paragraph. Okay. Exercise 4 is, we have to go back a little bit. Exercise 4 is to produce these points from this source input. Your job is to define a macro point that looked like this. This was the source, and you just write the TeX coding for point that produced this from Knuth, okay? This is to make diagrams, assuming that somebody's going to draw the lines in by hand, okay? Now, the next, fifth example is from this kind of you're supposed to define two macros in this case, one called write justify the following, another called end write justify. And this is for people who don't like to type a lot of, do a lot of keystrokes. So you want to set it up for the user so that a carriage return is good enough to recognize that there should be write justify. So typists would just say write justify the following. Probably you would shorten the name of that if you were actually in practice. And then typists would give as many lines as are to be write justified, followed by saying end the write justification. Okay, and this is the way it would come out. Now, in this example, suppose the person wanted to write justify a line that went 2 lines long. Well, then you could allow them to put a % at the end of one of these lines, and to get to the next line. Arthur?
Suppose one of the lines that was fit on a line in the source took 2 lines in the output. You want us to handle that?
It's just gonna stick out in the left margin. You follow the instructions. Computer doesn't worry about it. So this is not going to be. You don't have to make it into a paragraph. Just use rjust line. Rjust line is in BASIC, which accepts anything. Okay, that is the 5th exercise. And the 6th exercise, the source is over here, and I also had to add what I'm assuming is for the baseline skip and line skip between lines. But the text was, how do you do this? And then it did a V-centered H-align centering, producing the macro called line down. Look at this strange pile. And then it went down this way. Then if I did the same thing with V-centered H-align, but now line up, and at this stranger one, it gives me the line up. Now, what's the idea of this is that line down is supposed to produce a list to TeX that says L, carriage return, O, carriage return, O, carriage return, sorry, that's carriage return, K, carriage return, space, carriage return, at, and so on. Strange comes out strange, carriage return, because it was in brackets. But that's what actually this was H-aligned here. Because I told you how the line down was used. So the output of line down macro is supposed to be this. It's supposed to take its thing and string it out with carriage returns in between. Line up is the same thing except the opposite way. It'll come out period carriage return, E carriage return, and ending with the A carriage return. And that's the output of those macros.
Change param size to get this to work?
Did I change what size?
Param size, the depth of the recursive stack.
No, the way I've done it, it doesn't require more than about 5 or 6 of the of nesting. Yeah, Arthur.
Can we assume that there's a character doesn't appear in this mess?
$. Okay. You can assume that there's no $signs in there because they would be used for except for, of course, for a math formula, which would be allowed. Well, but you'd probably put it in braces if it were. So okay. So I guess you can assume no $signs, yeah, or something like that, yeah. All right. Otherwise, there's a solution, but it's more difficult. So, yeah, and I'm going to talk about how to solve these problems later on this week. So those are the 6 problems that are in the handout. And now I want to talk about how this magical centering operation can take place. And in fact, one of the things that I'm looking forward to seeing interactive TeX is to see how it would look to be typing in to this centering macro and I add another word, and then all the lines that shuffle around again and recenter themselves properly. That should be very fun to watch, and that could be built in. In fact, just the paragraphing mechanism of TeX is going to be built into our Sun terminal, so we'll have that ability in our editor anyway, I think. Now, All right, so let's take a look and see what we want to do now. Space between words. If I want lines to be centered, I better get my cheat sheet here. Okay, now. Okay, centered. Here we go. Oh no, I'm sorry, I got to find page 22. Here it is. Okay. Okay, so now I've got to put something at the beginning, and I'm going to say hskip. The very beginning of the paragraph will say no indent, and then it'll say hskip 0 point plus 1 1m. Let's say 10 point or 1m. Let's call it 1m of stretchability. That actually, that amount is, as you see, isn't going to be critical, but I'll use it now. Then, and then will come a word like in, and then there will come another space between words macro, in, olden, and then will be a space between words macro, and so on. So all my space macros, I'll just write control space, and we'll talk about how you get those in the paragraph later. But for now, let's just say that the spaces are all there. So that's the paragraph, and then I have to tell you what the spaces are going to be. Then finally, at the very end of that paragraph, there was the word plaything, and then at the very end, I'm going to at the end of the paragraph, I'm going to say again hskip 0 point plus 1m, and break and that'll be the glue that comes at the end of a paragraph. This is known as the par fill skip, and so you can set par fill skip to whatever glue is to be placed at the very end of a paragraph. The par fill skip would be set to that. Now, what about this space macro here? This is what goes on between spaces. And I'll first explain what it does, and then we'll see how to implement it. Now, this is going to go like the following. hskip 0 point plus 1m, penalty 0, hskip 1/3 m. That's the normal spacing between words, plus minus 2m, and then I'll give a h box of null, and then I'll say penalty 1000, and finally hskip 0 point plus 1m. All of that is one space. Okay. All right. Now, in TeX, there's a feature now called spec skip. You could define spec skip 1 to be 0 point plus 1m, and spec skip 2 to be 0.33m plus negative 2m's. And then you could say just here skip 1 and skip 2 to save memory inside of TeX and to save some writing. I mean, because you would have a lot of these spaces proliferating in the memory, and so this makes it much easier for TeX to refer to something where you have certain kind of glue that you're using over and over again. Anyway, that's just a slight optimization. This is what really goes in there for every space in the paragraph. Now, what is actually happening then? Well, I claim that TeX will never break at the first one, because it's always better to break at the second one, having a little bit more stretchability. Therefore, I'll consider two cases. It either breaks at this penalty or it doesn't. Notice it'll never break at this glue, because glue has to be following a box to be broken. And it will never break at this glue, because that's following a penalty, and it'll never break at this penalty, because the penalty is 1,000, which is the cutoff point. So the only chances are that it'll break a line between words or won't break a line between words. So we have to consider the two cases. First, what if it doesn't break a line between two words? Then everything gets added together. What happens? The pluses cancel, to 0, so there's no stretchability, and you have a skip of 3 of the normal space between words. So the words appear with their normal spacing, and there's absolutely no stretching or shrinking. The other alternative is to break here. Now, at that point, if you break at a penalty, remember it throws away the following glue until it gets to a box. And I put this box here to stop that process. It's an empty box, there's nothing in it, but it'll wipe away these two things. At the end of one line, at the end of the line, it'll say h skip 0 plus 1m. At the beginning of the next line, it'll have this empty box and h skip 0 plus 1m. So what's happening is I'm starting out every line with h skip 0 plus 1m. The first line was started with that. The last line is ending with that. I'm also ending every line with that. And in between, where I'm not taking breaks, there's no stretching or shrinking. So the total amount of stretching in every line, in every possible system of breaks, is exactly 2m's. And TeX will compute the badness by means of this formula. So there's really, penalties are 0. And so really what we're doing is looking at, badness is the cube of the amount of stretch of the amount of actual stretching that has to be done. There's no shrinking, so the lines will never get bigger than the margin. So what's happening is that if we're minimizing the over the whole paragraph of all possible line breaks like this, according to TeX formula, it turns out we're really minimizing the 6th powers of the distances from the margin to the text in each line. So it was sort of saying you start at the left-hand edge and calculate how far you went in there, and then take the 6th power of that, some constant proportionality, and find the set of line breaks of all the ways to do it that minimizes the sum of 6 powers. Well, minimizing the sum of 6 powers is almost exactly the same as minimizing the maximum of the numbers. So it really is saying finding the way to break so that the maximum distance from any left margin to the text is as small as possible. And that will produce the shortest number of lines, and that for which it's reasonable, and also make this centering effect. The reason it's centered, of course, is because we have the 1m stretch at the left, 1m stretch at the right. All right. That's the way TeX boxes, glue, and penalties can be harnessed to this strange job of ragged centering. Similar things, but easier, will give you ragged right, ragged left, and the effects of that we needed for Pascal were a combination of these two things. Now, I have to say, what about getting the spaces here? Now, it's a little. You could say, well, let the person type all the spaces in if he wants it centered, but well, that's a little bit of a nuisance. So there's two, there's at least 2 ways to do this, and one of them is to define, is to change the code of the space character to be type 13. So change code, that's octal 40 as a space character equal 13. This means then that whenever a space occurs, it gets changed into a control sequence with the space. This means that 2 spaces in a row would be recognized as a single space. However, Arthur?
Does that mean that the person would have to do the same thing with the carriage return?
Now, if you want a carriage return, then you would leave a space, and then you would probably put a % sign after a space at the end of each line. Or you could do the same thing with a carriage return. But carriage returns are tricky. The carriage returns are a little different from arbitrary symbols. The timing of getting the carriage return started and stopped, and the fact that a line does end with a carriage return, and sometimes the carriage returns are a bit of a nuisance. So this is one way that would convert all the spaces to that. Let me see. Is there another way? Another way is to use a process very much like the line down. Your solution to the line down problem here, or the line up problem, which would be to take the whole paragraph and let TeX just treat all spaces the way it usually does, and then the parameter or the argument to the line down macro would be a bunch of text with spaces in it. And then this by the same way that the line down takes that and puts carriage returns in front of it, this centering macro would replace all the spaces by this long ritual, and until it got to the end of the parameter list. So that's a safer way to do it without a change code instruction. Change code can sometimes lead to problems in inconsistencies between formats. Okay, now I've got 2 minutes left. Do I have a question, or should I launch into something slightly new? Okay. The first thing we'll be talking about tomorrow is the tools that TeX has for arithmetic. At first I resisted the idea of putting a programming language into TeX because everyone wanted to define this in computer science terms, but I wanted to have it more of a descriptive thing, so that the things you type into TeX look something like the document, and rather than like a program saying here's how you typeset the document and giving specific commands. However, by having macros, it's turned out that you can actually program TeX to do things by using macros to execute things. For example, a control sequence is like a variable. You can define it. That's like setting a value of a variable. You can not only that, but TeX has arithmetic. It's easy to add two variables together by putting them in counters. You can set if you have a variable, it can a control sequence can be defined to equal -30, and then another control sequence could be defined to equal 45, and you could write a macro that would produce a control sequence for the sum of those two control sequences. The difference is also easy because you can change the sign. Multiplication of integers, well, multiplication by 10 is pretty easy because you just add a 0 because we're working in TeX, you see. You can also reduce multiplication to repeated addition. So you can, and there's, as we'll see, macros allow you to have recursion. So it's pretty easy to write a multiplication routine. Division isn't that hard either because you can even multiply the divisor by appropriate power of 10 and subtract it as many times as you want, and you can figure out the quotient and remainder of two integers. What about floating point numbers in TeX? Well, you can also do arithmetic on those. You can add together two dimensions because you can say save 0 h box, and then you can say h skip by the first dimension and h skip the second dimension. Okay, and then look at the width of this box. It's the sum of the two dimensions. You can multiply dimensions because you can ask for 3.8 times the width of this box. 3.5 times the width of this box would be the product of some pure constant times a dimension. All right. You can divide dimensions because by repeated subtraction we have an if dimension command where you can test if one dimension is less than another dimension, and by recursion you can divide one dimension by another and get the integer part and the remainder. So actually there are ways in these macros to program something like working a Turing machine to bootstrap up and do operations that could have also been put in directly at the source level, but have snuck in the back door. Is there a question?
Yeah, one question. But with that way of adding, for example, by putting two boxes one after another, then boxing the whole thing and taking the sides, the result you get out has got a dimension on it. For instance, if you wanted that dimension will be...
It's some real number. It's some dimension. That's right. Some floating point quantity.
But it's got a dimension.
It's physical. It's a physical length. And so I don't get square inches off. But this is a physical length. It's a dimension, whatever. It's in units of physical things. If you put in millimeter and add 5 millimeters to 1 inch, you get some physical length, which is the.
So if you wanted to divide that by some other number, you'd have to...
I could divide one dimension by another and find the pure number, which is how many times the one goes into the other.
By subtracting, by adding a box of negative width of the other one and waiting...
And waiting until it drops down. Or I could subtract 10 times the... I could subtract 100 times the width of one box from another one until they weren't less, and then I could subtract 10 times and 1 time. I could get the quotient that way. Okay, so it's possible to do these operations by recursive use of macros, so that's snuck in. I guess the last thing that I could say today is then one little trick about what if you wanted to save 100 different dimensions and you wanted to get at the kth one? So you had an array of dimensions and you wanted to actually access the kth dimension, okay? Well, this is terrible, but I thought I'd end with this. So suppose I said save 0, h box, and then I give h skip first dimension, number 1, and then up to h skip number 100. So now I have 100 h skips in this box. Okay. Well, then to figure out what the kth one is, you do something like this. You unbox 0, and then you follow it by unskip the 100 minus k times.